Yeah, thank you so much for this opportunity. I'm Harikrishnan Ramani at Stanford, and I'm talking to you about Neutron lifetime anomaly and composite solution that we proposed with Sujit Rajendran last month. A brief tribute to the frontline workers, without which seminars like this won't be possible. They are real heroes. Here's my outline. So first, I'll briefly discuss the neutron lifetime anomaly, a theorist's view of understanding of what's happening there. And then talk about dark matter accumulation on Earth, and then tie them both up as an explanation, dark matter as an explanation to the neutron lifetime anomaly, and finally conclude. So the neutron lifetime, you're talking about a particle that was discovered almost 90 years ago in 1932. Its lifetime is roughly half the duration of the seminar, around 15 minutes. The simplest example of beta decay that we know. It is good to know the neutron lifetime very well, because if you knew it very accurately, you could extract things like the CK matrix element, VUD, without more complicated nuclear matrix elements, which are currently used. So more bigger nuclei beta decay are used to extract VUD. And the lifetime uncertainty is the main cause of uncertainty in the helium abundance predicted by Big Bang nucleosynthesis. So for this reason also, it'll be good to know what the neutron lifetime is. The question is, how accurately do we know it? And there are two ways to measure. So the first one is the beam method. So in the beam method, the lifetime is measured by counting the subsequent protons coming from the beta decay of cold neutrons. So when beam, please do not think, high energy particle physics. These are still pretty cold neutrons, around 40 Kelvin kinetic energy. So it helps to have them cold, because when they pass through this trap, they spend more time, and hence more protons are inside the trap. So the number of neutrons at any given point is inside this trap is counted by the subsequent lithium fluoride counter that's placed in this figure to the left of this counter, and the neutrons just flow out because they are not sensitive to the E and B fields. The protons instead, which are produced by the neutron decay, they are trapped inside with this large electric and magnetic fields, and then subsequently these protons are extracted, accelerated, and then counted. So this is called the beam method. In the bottle method, we are talking about ultra cold neutrons, much colder, traps of around 0.5 millikelvin, roughly 50 nano eV. And trapped neutrons are directly measured often. So you wait for some time for the neutrons to disappear, and then you measure the neutrons that are left. So that's how the bottle method works. The funny part is there is a long-standing, almost 25-year-old discrepancy now on disagreements between the bottle and the beam. And the beam has repeatedly measured longer lifetimes by around 8 seconds compared to the bottle method. And subsequent measurements, both in the bottle and beam, have been successful in reducing systematics, but to no avail. There still is this discrepancy that's approaching around 4 sigma now. Okay. What are the possible BSM explanations for this? I think the main explanation out there is from the observation that the beam measures protons and hence only the beta decay, whereas the bottle measures the inclusive decay, everything the neutron decays into. So then the natural question is, can you accommodate a BSM decay channel for the neutron to explain this bottle beam anomaly? And that was explored by Fornell and Grinstein and many other subsequent work. But the issue, of course, is that this is highly restricted parameter space. After all, if you introduce a new neutron decay channel, you need to make sure that the larger nuclei are stable. The larger nuclei are stable, after all, because of complicated nuclear physics inside, which prevents the neutron from freely decaying because of the presence of the protons. Our approach here is a little different. So just to finish that discussion, the solution requires a particle very restricted in just below the neutron mass in order to explain the neutron bottle anomaly that way. Our approach is different here. We want to ask the question, can the neutrons in a trap scatter with dark matter around us and disappear? So this is, and let's see what kind of numbers we are talking about. So just to recap, 50 nano eV trap for measuring UC and lifetime. Dark matter can kick neutrons off trap, affecting the measurement. So the neutrons just fly away, and you wrongly think the neutrons decayed, whereas they were just scattered away from this trap because too much energy was given to them by dark matter. Then if this is really successful, what you have in your hands is the 50 nano EV dark matter detector, albeit with small exposure. So just to put things in perspective, most direct detection experiments that work today, we are talking about thresholds of a few keV, right? There are exceptional ones like Sensei with smaller exposures that can do a few EV. We are talking about 8 orders of magnitude lower in thresholds with paltry amount of exposure nonetheless. So just to put things in perspective. So you can ask, how much and what cross section do we need to explain the discrepancy between bottle and beam? So just a bunch of different bottle results. I will mainly concentrate on the top row here, which does no extrapolation, whereas the rest use what are called some versions of a material bottle, and there can be neutron loss in the material. So they extrapolate between finite volumes and infinite volume to get the lifetime. And you see that the cleanest of them, which is the top row, also predicts the smallest lifetime among all these things. It's actually 877.7 seconds, whereas the beam results, to put it in perspective, is 888 seconds. Okay. How much dark matter would we need? So you just saw this equation. So there is a effective rate for dark matter scattering, and then there is a rate for the beam, and you want to sum them and then call that the rate for the bottle. So you have n sigma v plus 1 over the lifetime as measured by the beam is 1 over the lifetime as measured by the bottle. So if you crunch some numbers, the cross sections you would need are gigantic. We're talking about 10 to the minus 25 centimeter squares, abysmally large, and numbered in. Sorry. Hello. Okay. I'm going to continue. So cross sections of 10 to the minus 25 centimeter square and number densities of around 10 to the 14 per centimeter cube. So obviously this is no ordinary virial dark matter. We are not used to number densities like this or cross sections like this when we talk about dark matter densities. But have we seen large cross sections and densities before? Some of you might have in this talk on May 4th by Maxim Pospolov, where he showed some work we did together with Surjit on metastable isomers. So what is the idea here? Let's start with the large cross-section part of it. That seems much easier. And what are some model variations? A subset of you have worked on things like this, like heavy quark, standard model quark, hybrid hadrons with strong interactions, inspired by what gluinos would do in order to form dark matter. So here, dark matter interacts with the standard model through our SU3, through color. Another example is Millicharge particles, spurred by the recent interest to explain the edges anomaly. So you can read some of these papers here. One other example that's not been looked at too much is blobs with large range force. So inspired by standard model nuclei, if you have a dark sector with some confining force, it should be very natural to form these gigantic objects which carry large charge or whatever force the fundamental particle is charged under, and that should also be natural and should have large scattering with the standard model. So the question is, if these are dark matter, why are they still alive? After all, xenon has blown limits out of the park. We are several orders of magnitude below the strong scale, like even slightly lower than the weak scale. That's where we are sensitive to today. So there is absolutely no reason why these should be alive. And not so quickly, there is a caveat. And the caveat comes from this. If dark matter is too strongly interacting with the atmosphere or rock overburden, then it stops the dark matter from reaching the experiment with enough kinetic energy. So the atmosphere itself stops it, and it thermalizes rapidly, and you just do not see the energy in even a surface experiment. So I show this with two plots, both Millicharge parameter space, again just representative to show you that this is really possible. So the authors here are showing the ceiling. So we are usually used to the parameter space below. So this is around sub GeV scale, but a similar parameter space exists above a GeV in the right plot. But let's concentrate on the top here, the top of the orange, which points out that even for a surface detector, there is enough of an overburden where dark matter just does not reach Earth. Of course, the cross sections are really, really huge, 10 to the minus 20 centimeters square. With such huge cross sections, you can ask, hey, wouldn't I have seen this at colliders? The answer is you will not have. So these charges roughly correspond to around 10 to the minus 1 of the electronic charge you see in the right plot just below the gray region. And there is ample white space in between where dark matter can lie, and you wouldn't have seen it at all. Okay. And what happens to the shielded dark matter is the next question. This dark matter accumulates. With large cross sections, order 1 gets captured on Earth, and this can lead to large enhancements. What kind of enhancements are we talking about? Let's just take the best case scenario of where all the dark matter gets captured. Then you just put the flux times the cross section area of the Earth divided by the total volume. And when you divide it by the virial number density, you get this huge number, 2.2 10 to the 16. So instead of GeV per centimeter cube, for these crazy models of dark matter with large cross sections, you have instead of GeV per centimeter cube, you have 10 to the 16 GeV per centimeter cube. Those are the kind of numbers we should get used to in this talk to proceed forward. So just from putting the strong cross section, which was needed to explain the neutron model, it looks like you get the other guy out, which is the requirement of the large number density, right? And with this large number density, you would think, oh, this should have been seen already. But the issue, of course, is that this is thermalized with room temperature. So it has kinetic energy of 25 millieV. It's very small and does not show up in traditional direct detection. The next question is it useful? How much collects near the surface? So this is all good. It collects on Earth, but are there other effects? The first effect is evaporation. So this was dealt with in this 1805 paper. And they point out that if dark matter thermal velocity is larger than the escape velocity, then it will just start evaporating from the Earth, right? So you can go ahead, calculate what happens. And what you find is that below a GeV, you do not see this large number densities I predicted in the previous slide. It's only above a GeV that this works because of evaporation. Okay. There is a second effect, which is the Earth is not uniform. There is gravity that's trying to pull things towards the center of the Earth. There is temperature variations. There are density variations between the core mantle and the crust. And when you calculate this, again, the 1805 paper shows that dark matter heavier than a GeV sinks. So here they're plotting for you what the density profile of this collected dark matter looks like. And you see that for a GeV, it's near constant from the center of the Earth to where we live. Whereas for 10 GeV, the number densities are 6 to even 7 orders of magnitude lower. And for larger masses, they are even lower. So what this suggests is that there is this sweet spot of around a GeV that might work for us. Okay. So over the last couple of years, I've been thinking about this dark matter possibility and developed a few different ways to look for them. One of them was covered in Maxime's talk, where metastable isomers were used to look at these strongly interacting dark matter inspired by gluinos. But there are some ongoing projects. One of them is what are called electrostatic accelerators for Millicharge dark matter, possibility of using something like Luna to just accelerate Millicharge particles if they were stuck on Earth. Whereas this talk will be using this composite dark matter models to explain the neutron bottle anomaly. And one thing to point out is that all these models could one day be adequately covered by cryogenic detectors, which are, I'll be talking about them in a few slides. So why is this a good candidate for neutron bottle? What would be the salient features? Dark matter A is very slow. It has 300 Kelvin or kinetic energy of 25 milli eV, which is very small. But then the point here is that the neutron bottle trap is only 50 nano eV, so this is good enough for those purposes. It's much larger, orders of magnitude larger than the energy needed. We wanted high number densities and cross sections, which are both available, so it's perfect for explaining the neutron bottle, neutron lifetime discrepancy. And furthermore, let's couple the standard model with the long range force, then you increase the cross section at low momentum transfer. After all, this is the experiment with the lowest momentum transfer that could be designed for direct detection, and so the cross section will just only grow larger for a long range force for such really small momenta. So we will invoke a composite dark sector, the reasons for which will be clear soon. So the dark sector is formed by, consists of some dark fermion F, and it confines at some scale, say a few MeV or a little lower, a few keV, and it forms these big blobs with large NF. Okay. So with this construction, it should be very natural to see large charges G blob greater than 1. After all, if ignoring the electron in the standard model, you should see these huge nuclei with charges in the few tens. And there also, it's because of electromagnetism, it gets cut off, and then we do not have heavier nuclei. So this is not pretty crazy. I mean, this is pretty minimal, and then you could get pretty large NF out of such a model. And I'll take a long range force under which this is charged, MA of 10 eV. So this is just a Yukawa force. It could either be a U1 or it could be a scalar. I'll differentiate between these two in a while, but for now they are equivalent. I'll just take a vector for concreteness, and I'll couple that A to the standard model. After all, I want to talk to the neutron through a neutron dipole moment. Okay. Neutron electric dipole moment to be specific with this operator. Okay. This is my model. And immediately something is very clear. If I have this large NF and hence large charges, all of a sudden I have large dark matter interactions. Okay. And this kind of complicates and provides some novel phenomenology to this trapped dark matter. First, if the coupling with the standard model is large, then there's the vanilla dark matter trapping I was talking to you about earlier, okay? But then if you dial the coupling lower, there's an intermediate regime where there is some amount of trapping by the Earth. The slower velocity dark matter, because of the long rangeness of the force, it has much larger cross section. So there's a subcomponent that reigns in, that gets trapped. But then there is subsequent ejection due to self-interactions with the virial population in this intermediate regime, right? So virial dark matter that's super strongly interacting with itself with the thermal component, it has enough kinetic energy to just kick this thermalized component out, so you will not have a large buildup of dark matter. So to arrest this, we invoke blobs of different sizes. After all, that's also very common. Nuclei are not a single mass. You see them all over the place, and you should expect blobs also to be of that sort. Then the heavier population gets trapped easily because it has much larger charges and hence a larger coupling with a standard model. And the heavier population starts trapping the lighter population, which could be much larger in number. So the seed population created by the first dark matter, heavier dark matter that gets stuck on Earth, and subsequent light dark matter, this seed population is effective at trapping subsequent virial dark matter. You do not need a heavier population anymore. So once you have a critical density, you have an attractor solution, if you will, and you have all of the dark matter that's raining in on Earth getting accumulated. Okay. One more quirk of these large self-interactions is that while we saw that masses greater than a GeV sink very fast, self-interactions can arrest this, right? So repulsive, so you can ask, what is the largest number densities I can have with such large repulsive dark matter force. And here, of course, I'm invoking a vector to have this repulsive force. Then you just equate the potential energy with the room temperature, which is the kinetic energy, and you see that there is a maximum density for mediator masses of around 10 eV or so, and with couplings of around 10 to the 4 or so, which will be around the benchmark that I'll be dealing with. You have number densities of 10 to the 13 per centimeter cube. So the funny part is that you cannot have more than, say, 10 to the 13 per centimeter cube at the core of the Earth. Whereas if you sink dark matter, then there will be much larger number densities, like we saw a few plots ago at the core, which will not be possible in this repulsive model. So you will have near uniform number density. Of course, I say a near uniform because there are temperature variations which change this total number density, but this can effectively prevent sinking, and even for larger masses, it can provide support at the crust and near us. Okay. So some more facts about the blob. The blobs have non-zero radius, because after all, nuclei have non-zero radius. And as we know, they scale like 1 over lambda, in our case, 1 over lambda QCD, in this case, 1 over lambda dark, where the confining happens, and NF to the 1/3, where NF is the number of fermions inside this blob, right? And what this implies is that just like the Helm form factor, when we do dark matter nuclear scattering, if we are doing blob scattering with a neutron, there is only coherence at lower momentum. If you go to larger and larger momenta larger than 1 over the size of the blob, you start probing the blob itself, so you start losing coherence. And as a result, this long-range force further prefers, the long-range force, of course, also further prefers smaller momentum transfers. So it provides this nice window where only small momentum transfers are allowed, which we'll exploit soon. Just to see what kind of parameters are allowed, here's my Lagrangian again. And the cross-section to scatter with a neutron from the trap is given by this expression, dq squared d sigma dq squared. And I'll integrate, of course, from q min, the minimum momentum I need to excite the neutron from the trap, and the maximum momentum, which is either set by the momentum of the center of in the center of mass frame, or our blob, which is the size of the blob, which we just saw in the previous slide. And with this, we obtain, apart from this log, just g blob square over lambda, which is the dimension 5 operator here, lambda square v thermal square. Okay, so this is what I obtain. However, there is this log q max over q min type behavior. So if you squeeze q max and q min, you will have smaller and smaller cross sections. So this gives me 10 to the minus 34 centimeter square g blob square, and I will show you some plots soon. But finally, you have g blob of around 10 to the 4, so pretty large. We are not talking about order 1, and that is part of the reason why we need composite objects. So we're talking about 10 to the 4, 10 to the 5 for surface densities of around 10 to the 14 for GeV mass blobs. Okay. So this is where this parameter space lie. Just to recap the model, blobs are made of dark matter fermions. The blob charge here is G blob. This is much larger than the individual fermion charges, so do not worry too much that this G blob is much larger than 1. And the neutron dipole moment, the lambda, is chosen just to be below the supernovae bounds, so as to not get ruled out by just the mediator cooling supernovae too fast. Okay, and the mediator mass I will explain in a while. In a few, it's not that important to this plot. The mediator mass can be moved around, and this is totally okay. But the red and blue, the red refers to where the repulsions set the local number density. And if you ignore repulsion, suppose you model build it away, or these blobs also have their negatively charged counterparts somehow screening, you can complicate the model. And if you ignore these repulsions, then you have the blue. And the blue, of course, predicts a sweet spot around GeV, because masses above a GeV, you start sinking. Whereas when repulsion set the local number density, as we pointed out, sinking is effectively prevented, so you have a much larger parameter space. So this by the way, naturally comes out of these repulsive self interactions. So I've not put in anything extra by hand. It just naturally came out. Okay. And not only for f equals 1, you can go to much larger, much smaller fractions of dark matter. So there is all of dark matter around us, but only a subfraction of it could be made of blobs. So this is for f equals 1. There possibly are bullet cluster constraints on self-interactions for f equals 1. But as soon as you go to even say 5%, these self-interaction constraints go away, and 5% of dark matter is very poorly understood. So I'm imagining living somewhere up here, so around 10 to the 5-ish. Couplings, but of course they can be natural in these blob models. So this is the parameter space. There's one more line to be explained here, which is the stability. So remember that the size of this blob in some sense restricts the maximum momentum transfer above which you start losing coherence, and that momentum transfer should at least kick the neutrons out of this trap. And that is this line. And above that, your tuned stability, because you can imagine another long range force that has nothing to do with the neutron bottle scattering at all, that somehow provides the stability. It almost effectively cancels the surface energy density for these nuclei and keeps things stable. So above that, this model is tuned, but below that, there is still a lot of parameter space that could explain this neutron bottle anomaly. Okay, how would we look for this elsewhere? One place is DC heating. After all, these guys are at around 300 Kelvin. Suppose I have a fridge and this dark matter starts leaking into that fridge. This fridge shouldn't be cool anymore. All your insulation will not work for this dark matter, which has mean free paths longer than most of standard model, right? So the good place to look at is dilution refrigerators. They're ubiquitous in these cold experiments that the experimentalists use. So you can ask a question: local dark matter deposits energy on the component that's kept cold, and the stability of cold component gets at limits on DC heating. The current limit, so this is again private communications, there is not a paper yet, is around 63 nanowatt per mole in copper. Okay? So let's see what limit that sets, how much of the parameter space gets removed. So here I'm plotting in green contours for different mediator masses for blobs that would explain the neutron bottle anomaly, what kind of heat they would cause in copper, and those are in green. And Q max, which is the x-axis, is set by the inverse size of the blobs. So above that inverse size, you cannot have you do not have much coherence as we talked about. And in pink, I show the current limit from dilution fridges, and you see that a lot of the parameter space above Q max around 150 EV is ruled out. So there is this nice parameter space where Q min is around 10 EV and Q max is around 100 EV. That's not ruled out, and that will explain the neutron bottle anomaly. And ongoing work, 10 to the minus 12 watt seems to be possible. So of course, this DC heating, this just came out of just building a dilution fridge. You could think of designing something specifically to look at DC heating itself, and it seems that 10 to the minus 12 watt seems feasible at the surface, and 10 to the minus 16 watt deep underground. So this is ongoing work, and if this 10 to the minus 12 watt is successful, you see that it'll take out all of this parameter space by a few orders of magnitude. So this is testable in the near future, this model to explain the neutron bottle anomaly. Regardless of whether the anomaly persists or not, it's important to notice that this is a new test for local dark matter. There are not many other ways to see these blobs. They're just very annoying. At colliders, you see the fundamental fermions rather than these blobs themselves. Same is true about things like supernovae, where these fermions are produced rather than the blobs. And these blobs collect on Earth, and then they just lose all their kinetic energy. It is fascinating to know that the neutron bottle, with this tiny exposure, we were talking about few minutes compared to say a ton year for xenon, but it could still be sensitive to dark matter. And if this anomaly goes away and there is agreement between beam and bottle, you see that any region above this curve starts becoming an exclusion plot, right? Rather, the line, of course, explains the anomaly. Any region above that line is already an exclusion plot, and you'll start doing better if the anomaly disappears. Okay, that's all I have. I'll conclude. Persistent discrepancy in neutron lifetime between bottle and beam methods. Large accumulation of dark matter blobs is possible due to large interactions and self-interactions. Thermalized blobs can kick neutrons out of bottle, explaining this anomaly. And future cryogenic detectors could possibly test this parameter space. Thank you.
Thanks for an interesting talk. Questions? I have a question, actually. So yeah, has anyone done this neutron bottle experiment deep underground?
Deep underground. So so like in a deep mine?
Yes. So I mean, you are telling about the possibility that dark matter may not diffuse deep enough underground, so maybe you will see a difference.
So sorry. So that's a very good question. So in the case where repulsion set the local number density, density is near constant on the crust because there are no temperature variations in the height that you're talking about here, deep underground versus close to surface. In the case where you ignore repulsions, so you could. You need to model build this a little bit, the blue curves here. There, you could see minor variations in height. But even in that case, deep underground was a surface. The number densities are not that different. Maybe I gave the wrong impression here. The comment was never that there is no diffusion towards the center of the Earth. There is always diffusion, even in the GeV case. Almost all of the Earth is populated with dark matter. If you see this plot by Glenis Farrar and co, you see that from the center of the Earth to the surface, there's a near constant amount of dark matter. It is true that in this case here, of course, self-interactions are ignored. You see that there is a gradient. And you're absolutely right that you could somehow write this gradient when you go from surface to deep underground, and there'll be changes in density. And if this model is true, then the neutron lifetime will be different between deep underground and surface. But to my knowledge, most of the experiments have been done very close to surface. And so yeah, you're absolutely right. In that particular model, there could be variations.
I mean, the bottom line is basically that there isn't like that much of a change in the radius, right? You're kind of looking at, 6,000 kilometers is the overall scale height, and these things typically go maybe, a kilometer or two underground. So there isn't like that much of a variation in our model.
Okay, thanks. Any more questions?
Sorry, but you can go up in the top of a mountain.
Yeah.
Yes, that is a good point. If you get high enough to a region where the atmospheric density or whatever is low, so if you try to do it in a balloon for somehow, right, where there isn't that much captured, that would indeed be an interesting thing to try.
But I guess you need to build an ultra cold neutron source on that mountain to do the thing. It's not a quote unquote tabletop which you can take anywhere. But yeah, I don't know how feasible building a new source is. Yeah. So once again, in the model where repulsions are important, this thing fluffs out, and the density again is almost entirely set by the local temperature. So in that case, even going up a mountain might not be very useful unless there are drastic decreases in temperature. The decrease in temperature will help, how does it go? Will help decrease the local number density of dark matter, because you can now
anyway, if they did that, I mean, who cares about a specific model, right? But if they did that experiment and they found that at higher altitude, the anomaly went away.
Right.
That would anyway be an interesting check, right? Like,
yeah.
Because typically what is often said is some stuff about how the bottle has, various leaks or something like that. That's what you normally think about. But here, all of those systematics would be common. It's just the fact that the scale height would change, this particular thing. So
agreed.
Yeah.
More questions, comments? If not, then thanks again for an interesting talk, and thanks to both speakers. And please be back on Tuesday.